Hello, we are discussing about GATE 2007 ECE paper, and the topic we are discussing is electron devices. This is a common data question which includes 3 sub-questions. Look at the diagram. The figure is a capacitance voltage plot. The figure shows high frequency capacitance voltage characteristics of MOS capacitor, which has an area of 1 into 10 power minus 4 centimeter square, and permittivities of silicon and silicon dioxide are 1 into 10 power minus 12 farad per centimeter and 3.5 into 10 power minus 13 farad per centimeter respectively. First sub question. The gate oxide thickness in the MOS capacitor is A 50 nanometer, B 143 nanometer, C 350 nanometer, D 1 micrometer. Correct answer for this question is 50 nanometer. So from this plot we are going to calculate the gate oxide thickness. First of all, we have to study something about the gate oxide plot, that is capacitance voltage plot of MOS capacitor. Then we can solve this problem. So we'll look into the details now. A MOS capacitor is formed with the help of metal, oxide and semiconductor. Metal acts as gate, oxide is nothing but silicon dioxide layer, semiconductor is nothing but substrate, which is also called as body or bulk. So whereas metal and semiconductor act as two parallel plates and oxide layer act as dielectric material between two parallel plates. So a simple MOS capacitor looks like parallel plate capacitor, and the distance between the parallel plates is nothing but thickness of oxide layer, which we are going to calculate. It is indicated with TOX. So this is TOX, which is thickness of silicon dioxide layer which act as dielectric material. So for the MOS capacitor shown previously, we can apply gate voltage. The gate voltage can be negative or small positive or large positive. So if we are going for the first case, if the gate voltage is going to be less than 0, we call it as, in technical terms, if gate voltage is less than flat band voltage. By that time gate voltage is negative and MOS capacitor is said to be in accumulation mode. That is, whenever we are not applying any voltage, the p-type substrate body, here the semiconductor we are going with is p-type substrate. In this p-type substrate, holes are going to be majority charge carriers, and this region near SiO2 layer is called as normally channel region. Near SiO2, this region is called as channel region, that will be consisting of holes only if you are not applying any voltage. Now if you apply negative voltage, that negative voltage is try to attract positive charge carriers from the substrate. Positive charge carriers in the p-type substrate are holes. Holes are attracted towards silicon dioxide layer and they will be accumulated in the channel region, because they cannot move into the gate side since silicon dioxide act as insulator. So all those holes are going to be now accumulating near the channel region. Previously, how many number of holes we have at 0 voltage? Now we have more number of holes compared to 0 gate voltage. So that's why more holes have been accumulated. That's why it is called as accumulation region. In this accumulation region, the holes in the channel act as second parallel plate, whereas gate act as first parallel plate, and in between silicon dioxide act as dielectric material. So a simple parallel plate capacitor is formed between gate and holes in the channel. So this is one parallel plate, this is second parallel plate, in between there is a capacitor existing. Because of this one, a capacitance exists, and the distance between these two things is nothing but COX. So the COX can be calculated by using a formula for parallel plate capacitor, that is epsilon A by d. D is nothing but distance between the plates, but we can write COX is equal to epsilon A by TOX, oxide thickness. Here epsilon implies nothing but epsilon naught into epsilon r. Epsilon r is relative permittivity. That relative permittivity you should take care of silicon dioxide, not silicon. So in the accumulation mode, the capacitor is simply act as simple capacitor with capacitance value as COX. Now if we apply gate voltage, a small positive voltage, when we apply a small positive voltage that is greater than flat band voltage but less than threshold voltage, then the MOS capacitor is said to be in surface depletion region, simply depletion region. What is meant by this one? If we don't apply any voltage, by that time the majority charge carriers present in the channel are holes, because we are dealing with p-type substrate. Whenever we are applying a small positive voltage, that small positive voltage is able to attract small negative charge from the substrate. Negative charge in the substrate is nothing but, we are using p-type substrate, negative charge is nothing but electrons. That is, minority carriers in the substrate are going to be negative charge carriers that will be attracted towards channel region. But already holes are present at 0 gate voltage. Now the electrons are coming towards channel region. These electrons recombine with the holes present in the channel first, so that hole electron recombinations are taking place. That is going to be giving a negative ion, so that this negative sign implies nothing but these are ions. Negative ions are going to be created in the region. Negative ions are going to be immobile, so they stayed like that only. There are no mobile charge carriers present, so that is treated as depletion region. So now the depletion region is going to be formed for a small positive voltage. For small positive voltage, small number of negative charge can be attracted. That small negative charge is going to be recombined with the holes present in the channel region, so that it becomes negative ions will be created in the channel region. That region is going to be now called as depletion region. So at this point, the capacitance can be seen in this way. The depletion region is also now acting as dielectric material, so entire width is going to be now increased, that is the distance between the plates. Now also this p-type substrate is going to be acting as one parallel plate, the gate is acting as another parallel plate. Distance between the plates is now increased. Previously there is no depletion region, holes were present over this place, but now holes are going to be over here, p-type substrate, and now the parallel plates are going to be differed by a large distance, so width is going to be increases. That implies oxide capacitance, overall effective capacitance is going to be reduces. So as you are applying more and more positive voltage but less than threshold voltage, this depletion region is going to be increases, so that effective capacitance gets reduces till threshold voltage is going to be applied. So in the depletion region, the MOS capacitor consists of two capacitors in series, as you have seen. One is the oxide capacitor COX, and the other is nothing but depletion layer capacitance C depletion. If we add both the things at that time, that is the effective capacitance between gate and substrate. Now if you will see what happens if you apply sufficient large positive voltage. So that effective capacitance can be written as like this: 1 by C is equal to 1 by COX plus 1 by depletion. MOS capacitor biased into inversion. Whenever we apply sufficient large positive voltage that is going to be greater than threshold voltage, then the MOS capacitor is said to be in inversion region. In this inversion region, we are applying more positive voltage, so that initially a depletion layer is formed, and after the depletion region, the more positive since we are applying more positive voltage across gate, now gate is biased with large positive voltage, so it can attract more number of negative charge carriers from the p-type substrate. That is, more number of minority carriers are going to be attracting towards gate side, so that out of that large negative charge, few are going to be recombined with the holes present in the channel, so that a depletion region is going to be formed. As we discuss, the remaining negative charge carriers are going to be attracted towards silicon dioxide, and they will stay in the channel region, and that negative charge is going to be act as a channel. Now the channel is going to be consisting of negative charge carriers, that is nothing but electrons. Previously the channel consisting of holes if you are not applying any voltage, but if you apply large positive voltage, the channel is going to be turning towards consisting of electrons. So previously holes positive charge, now it is electrons negative charge. Inversion. That's why this region is going to be this bias condition is called as inversion region. Now the capacitance is going to be, now we are going with two different types of charges. One is nothing but inversion charge, which consisting of electrons. This is circle with inner dash implies nothing but they are electrons, and these are going to be negative ions. At this point, how to analyze the capacitance? The capacitance can be analyzed in two different conditions. One is at low frequencies, the other is at high frequencies. So at low frequencies, whenever we are applying low frequency signal at gate, at that time it is almost equal to DC conditions only, so that the inversion charge whatever you are getting over in the channel, it is almost constant, it doesn't vary much for the low frequency signals. Whenever it doesn't vary much, this inversion layer charge, that is electrons, is going to be treated as constant, and they act themselves as a second parallel plate for the parallel plate capacitor. So now if you see, this is gate and it is going to be treated as negative charge that act as another parallel plate. So now the distance between these two things is nothing but silicon dioxide layer thickness. So again the capacitance at DC conditions or at low frequencies will be equal to COX only, because the depletion region is going to be acting as constant and this negative charge is going to be acting as another parallel plate, so that this will be treated as COX, which dominates. So at DC and low frequencies, inversion charge is almost constant, so it acts as parallel plate. That inversion charge now acting as parallel plate, thereby capacitance is almost equal to COX. Next, at high frequency. At high frequency, if we change this gate voltage, as the frequency changes, the gate voltage is going to be applied very rapidly, so that negative charge varies. Whenever negative charge varies, we cannot call it as conductor. So negative charge varies, along with that one depletion region is also varies. So the width of depletion region along with inversion charge is going to be varies. By that time, p-type substrate act as second parallel plate. So at high frequencies, inversion charge thereby depletion region varies with applied input voltage. Now p substrate act as parallel plate, thereby capacitance at high frequencies reduces. Since it is parallel, p substrate is one other plate and gate is one plate, the distance between the plates is increases, so that capacitance is going to be reduces, because as the distance between the plates increases. Now these are actual MOS CV characteristics, capacitance voltage characteristics at any frequency, which includes low frequency as well as high frequency. Till now whatever we have discussed, we have drawn with this one. Whenever we are applying the gate voltage which is less than flat band voltage, that is whenever negative voltage is applied, then effective capacitance is COX. So this first implies nothing but it is related to the gate voltage less than flat band voltage. By that time, this is voltage scale VG, gate voltage, and this is flat band voltage. If the voltage, gate voltage is less than flat band voltage, that is nothing but this region. This region is called as accumulation region. Over that one, the effective capacitance is equal to COX. So this is COX. So whenever Vg is less than Vfp, at that time the mass capacitor is in accumulation region and the effective capacitance is equal to COX, first region. Next, whenever we apply gate voltage greater than flat band voltage but less than threshold voltage, by that time the depletion region is going to be increases. Whenever the depletion region increases, distance between the plates is going to be increases. Whenever the distance between the plates is increases, at that time capacitance reduces. As you apply more and more positive voltage but less than threshold voltage, depletion region increases, so that effective capacitance reduces. This is the minimum capacitance we are getting. This is maximum capacitance under accumulation region. Maximum capacitance under accumulation region, minimum capacitance in inversion region. Next, whenever the gate voltage is more positive, that is if it is greater than threshold voltage, by that time at low frequencies the inversion charge act as second parallel plate, so that again the effective capacitance will be equal to COX at low frequencies. And at high frequencies the inversion charge as well as depletion region is going to be varies, so that we cannot consider inversion charge as parallel plate. Now the p-type substrate act as parallel plate. By that time distance between the plates is going to be increases, so effective capacitance is going to be reduced. So this is what the this is what the capacitance at high frequencies. So at high frequencies the capacitance is going to be reduces. So we will get maximum capacitance under accumulation region and minimum capacitance at the inversion region at high frequencies. At high frequency capacitance is maximum in accumulation region and is minimum in inversion region. Since in our question the diagram is given for the high frequency, we are concentrating on high frequency. So we are indicating it as C maximum and C minimum. C maximum occurs in accumulation, C minimum occurs in inversion. At high frequencies we can write C maximum is nothing but COX, which is nothing but same. C maximum is nothing but COX, which occurs in accumulation. And C minimum is going to be, look at this one, C minimum consisting of two capacitances in parallel, that is one capacitance is COX, the other in series. One capacitance is COX, the other capacitance is C depletion. Both capacitors are in series. Whenever they are in series, we can write the equation like this: 1 by C minimum is equal to 1 by COX plus 1 by C depletion. So minimum capacitance is nothing but, from this third diagram we can write it as 1 by C minimum is equal to 1 by COX plus C depletion, because C minimum is series combination of two capacitances, one is COX, the other is C depletion. Now we are coming to our question. So this was the problem given in, this was the diagram given in the question, which is nothing but 1 picofarad and 7 picofarad. 7 picofarad is maximum, 1 picofarad is minimum. So whenever the voltage, gate voltage, this is gate voltage and it is capacitance. If the gate voltage is going to be less than 0, such that it is in accumulation mode, by that time we will get maximum capacitance COX, 7 picofarad. Whenever it is in inversion region, we will get minimum capacitance, which is equal to 1 picofarad. That is the meaning now. So the given parameters are: area is given 1 into 10 power minus 4, epsilon silicon is given 1 into 10 power minus 12 farad per centimeter, and permittivity of silicon dioxide is 3.5 into 10 power minus 13 farad per centimeter. We need to calculate the gate oxide thickness in the MOS capacitor. Gate oxide thickness in the MOS capacitor will give rise to COX capacitance, oxide capacitance. Oxide capacitance is going to be occurred in accumulation region at high frequencies. So at high frequencies accumulation region is nothing but whenever the gate voltage is less than flat band voltage. This is the diagram we have discussed. So COX is nothing but C maximum. C maximum is nothing but COX, which can be calculated by using epsilon A by TOX. TOX is distance between the plates, that is oxide thickness, which we are going to calculate. This epsilon we have to consider it as epsilon silicon dioxide, because we are dealing with SiO2 layer, into A by TOX. So COX is equal to, given it as 7 picofarad from the diagram. is equal to epsilon silicon dioxide. Permittivity of silicon dioxide is 3.5 into 10 power minus 12 into 1 into 10 power minus 4 by TOX. After simplification, we will get the oxide thickness as 50 nanometer. So the right answer for this question is 50 nanometers. Thank you.